Welcome back to Calculus 1. In this lecture, we're going to finally introduce some of the alluded to shortcuts for calculating derivatives. We're no longer going to rely on the limit definition, but within this lecture, we'll finally use the limit definition for the last few times to turn that into more efficient tools, some rules for calculating derivatives. All right, now we've done a few examples applying the limit definition to find the derivative of a function, and it is, moderately tedious for most functions. Anything with kind of a lot of powers of x, like we have here, would be kind of brutal with the limit definition. Now, it can be done, but I highly advise against that. This is going to be incredibly tedious, and what we're going to learn in this lecture, there, as it turns out, is a shortcut to finding a derivative for this function f of x, this degree 5, fifth degree polynomial. And this is where in the course we're going to start to introduce what we'll call differentiation rules. Now, just to be clear, we're going to break this into kind of 4 parts. The 4 parts being four very simple functions: constant functions, powers of x, polynomials, and then exponential functions. And these all have simple rules for their derivatives. You might be wondering, why don't we then just start the course with them, bypassing the limit definition? Well, we're in a mathematics course. We proceed logically. So we have some basic tools, the limit definition, and then we use those results, theorems, axioms of mathematics to get more results. So we're going to use the limit definition the last few times here to get new rules, and then we'll pretty much never rely on the limit definition again. All right, with that in mind, let's get into the first part: how to find a derivative for a constant function. All right, this, as it turns out, it's really simple, but we'll treat it as its own part. The function we're going to be working with in calculating its derivative is f of x equals c, where c is a number. So let's interpret this graphically. The equation y equals c, y equals a number, that's the equation of a horizontal line. So graphically here, the graph of a constant function is just a horizontal line. Now remember earlier, we mentioned it very briefly, but I'm going to try to explore topics with you kind of in 3 different ways: numerically, graphically, and algebraically. This graph here will give us kind of a graphical understanding of the derivative of a constant. Just think, what's the slope of a horizontal line? 0. So we'll see that referenced momentarily in a few seconds. All right, so let's apply our limit definition. We're using the function f of x equals c, where c is just some arbitrary constant, a number. All right, now this, as it turns out, with the limit definition for the derivative is really simple. Doesn't matter what you plug in as input to a constant function. Here, this constant function, every output is the same number, c. That's why it's called a constant function. All the outputs are the same constant value. Here, c. So if we apply the limit definition, f of x plus h equals c, f of x equals c, c minus c, anything minus itself, equals 0. So the limit definition here for the derivative of a constant gives that, well, it comes out to 0. So if our function f of x equals c, f prime of x, the derivative, equals 0 for all values of x. All right, now let's kind of understand that in some different ways. First, we can rewrite that using Leibniz notation, this differential notation, which we'll often use for stating differentiation rules. So this just kind of more concisely states that the derivative of a constant equals 0. Instead of labeling the function f and its derivative, f prime, we state it all concisely and compactly here in Leibniz notation. All right, we can also understand this kind of thinking of in terms of the slope of a tangent line. Earlier, we briefly recalled that the slope of a horizontal line is 0. Now, to make the connection, recall derivatives can be interpreted as slopes of the tangent line. Well, just take a look at the graph up there. Doesn't matter what point you pick on the graph of that constant function, every point on that graph has a horizontal tangent line. And just think what the slope of a horizontal line is, 0. So no surprise that now our derivative is identically equal to 0 or always equal to 0 for every value of x. Since graphically up there, every x value to that graph has a tangent line that is horizontal. All right, now there's a nice physical interpretation of this result. Again, we'll just try to look at this multiple ways. So let's interpret the constant function. Let's interpret our function as representing position. So here we can say our position, the function, s of t if we want to introduce notation, the position is constant. We can basically mean that's we're just not moving, we're stationary. And if your position is constant, well, your velocity is 0. Recall, we have this relationship. Velocity is the derivative of position. Velocity is the instantaneous rate of change of position. So we get this physical interpretation. If your position is constant, your velocity is 0. Again, a lot of different ways to interpret the derivative of a constant equals 0. All right, let's take a look at some examples. So let's say we have for the first one here, f of x equals 5. Any guess what the derivative is? 5 is a constant. The derivative is 0. All right, let's go to a different constant. Let's say f of x equals negative 1,000. Still a constant function. What's the derivative? 0 again. You can probably see the pattern here. Let's just hammer it in with a few more. Let's say your function f of x equals e. Notice this is not e raised to the x power. Here, e is just a number. It's approximately 2.72. What is the derivative of a constant? Well, 0 still. All right, let's say we have here one last one. Let's say we have the constant function 2 raised to the 100th power. Now just be careful. We're using exponential notation here. We have notation denoting an exponent, but there's no variables. This is not x raised to the 100th power, nor is it 2 raised to the x power. There's no x, no variable. 2 to the 100 is a constant. It's some number. Now it's really huge. It's absolutely enormous, but it is still a constant, just a number. And what is the derivative of a constant? 0. So as we go through some examples within the remainder of this lecture, which we're going to be splitting into a second and third parts, I'll try to intentionally trick or fool you with some examples here. Notation dealing with base e, exponential notation here, 2 to the 100. And I want to make sure you can understand why certain functions have derivatives of what they are. So just be careful to interpret your function correctly. Here, 2 raised to the 100th power is a constant. Okay, so that's really it for part 1. Constant functions, their derivative is always 0. So we can move on to the next part, part 2, powers of x. And this is where it gets a little more algebraically intense, but still manageable. All right, so we're going to be looking at a power. More formally, this is what's called a power function. You typically see them in pre-calculus. The function is written as f of x equals x to the nth power, where you interpret n to be a positive integer. And the reason why we're mentioning this is you can build up polynomials with power functions, powers of x squared, x cubed, x to the 4th, so on and so on. All right, now, again, we could just state what the derivative rule is here, but I kind of refuse to do that. I want to make sure you build your mathematical foundation. So let's kind of take a look at a few examples just to see why the rule, whatever it is, works out to be what it is. All right, so let's start with the simplest power of x. Let's say we look at the function x to the 1st power. Now for the next few examples, as we click through here, I'll put the work with the limit definition down in the lower left there. So if you want, pause, give yourself an attempt at this, apply the limit definition to calculate this derivative, where the function f of x equals x. Now, it's actually really simple. Notice in the work there, in calculating the difference quotient, x plus h minus x, well, that just cancels out and leaves you with h in the numerator. H over h is 1, so here the limit definition gives 1. This goes really quick. So when our function f of x equals x, or x to the first power, the derivative works out to 1. Make sure you understand that as coming from the limit definition. This is one of the last times that we'll actually apply the limit definition. All right, let's move on to a next example. So let's say our function f of x was x squared. We've done examples like this earlier with the limit definition. And if you work that out here, using f of x equals x squared, little more work, but still manageable. The limit definition from the derivative gives us coming out to be 2x. So again, pause if needed and work that out algebraically with your algebraic tricks. Remove the indeterminate form, simplify it. Shouldn't be too bad for you to verify that you get 2x as the result from applying the limit definition of the derivative. All right, so that's still within the realm and scope of this course. I think a student going through the calculus sequence shouldn't have any problem with, for instance, applying the limit definition to a degree 2 polynomial here. All right, let's go up to x cubed. This is where it's going to usually be the limit to what's sensible for me to see with your work by hand. You can start to see here it's a little more tedious, actually a lot more tedious, to start multiplying out and expanding x plus h cubed. Here, if you apply the limit definition to the function f of x equals x cubed, notice it's a lot more work to expand x plus h cubed than it was to FOIL or multiply out x plus h squared in the last example. Now, this is again, the kind of limit. Personally, I would not require one of my students by hand to work out the limit definition with anything above a degree 3 polynomial. This is basically as bad as it would get for applying the limit definition. So again, pause the video, work this out. Expanding x plus h cubed is going to be tedious, but you will get 3x squared at the end of that calculation, calculating the derivative with the limit definition. Okay, and again, that is the kind of limit of what I would expect algebraically for one of my students within the calculus sequence. Now we're just going to take a look at one more example if you're up for the challenge, the algebraic challenge. Let's go to x to the 4th. To be clear, this is, in my opinion, too tedious to include as a quiz or exam question in one of my calculus courses. If you can expand x plus h cubed, which you all can, you can expand x plus h to the 4th. You just need a little more time. And again, we're in calculus. I want to make sure you are tested on calculus ideas, not algebra ideas. So expanding x plus h to the 4th, that's really of no concern for me. All right, if you were to do this, again, it's really tedious. The end result of the limit definition, you do get 4x cubed. All right, that might take a while, but you will get 4x cubed at the end of that. Now, at this point, we kind of have enough examples to maybe observe a pattern and do what's called generalizing. Can we take these results and generalize them to an arbitrary power of x? So let's say instead of applying the limit definition or finding the derivative of x squared, x cubed, or x to the 4th, we're looking for the derivative of x to the n, where n is some positive integer. Now, if you take a look at the 3 examples there, the derivatives of x squared, x cubed, and x to the 4th, you might be able to start to observe a pattern. Notice the original exponents. These are the powers of x in the function, 2, 3, and 4. Well, in the derivatives, f prime of x, 2, 3, and 4 are in front. They're coefficients. Another pattern to observe with respect to the function and its derivatives there is the function has, for instance, x squared. the derivative contains a power of x that is one power less. X squared, notice the derivative has x to the first. X cubed has x squared in its derivative. And x to the fourth has x cubed in its derivative. Now, if you combine those two ideas, something about the original power coming down as a coefficient, and then something about the exponent being subtracted by 1, well, you might be able to generalize this. I'll pause one last time in case you want to write down a guess for the formula for what the derivative of x to the n is. And if you guessed n, that's the power coming down as a coefficient, and then the exponent for the power of x is 1 less. As it turns out, you guessed right. That is the correct formula. Now, in mathematics, this is kind of how we kind of start with research. So here we have a result that seems to be true, but can we prove it? So here, with enough kind of data from these examples, we would observe a pattern, propose this, and then we would try to prove it. Now, the proof is beyond the scope of the course, but it's probably accessible to some of you if you know the binomial theorem and other related ideas. We're not going to cover that, but that's just to build a solid mathematical foundation. So if you were to prove this, well, it turns out to be correct, mathematically speaking. All right. Now, I want to kind of just go back up to the first example in the table with the function f of x equals x. This seems to break the pattern, but notice if we rewrite the derivative, recall the derivative of x was just 1. Rewrite 1 as a power of x. You can rewrite 1 as 1 times x to the 0. What's anything to the 0 power? 1. So if we rewrite the derivative, instead of it just written as 1, let's rewrite it as 1 times x to the 0. Notice this derivative does fit the pattern. The original function was x to the first power. And notice in this derivative version that we expressed in red here, the power 1 has come down as a coefficient. The original function was x to the first power, but the derivative, we subtract 1. 1 minus 1 gives you this new exponent of 0. So by rewriting our derivative from 1 to 1 times x to the 0, we see that this formula, what we're going to call the power rule, is consistent. And that's kind of an important thing for mathematics, that results that we want to use are true kind of for all possible values. All right, let's go ahead and formalize this. This is what we're going to call the power rule. It is one of our differentiation rules, but it's not one of the big three for the course. The big three differentiation rules that we're working towards are the product rule, quotient rule, and chain rule. And we'll be getting to those shortly, but not within this lecture. That's basically what comes next. All right, so the power rule, as we've kind of arrived at it here, the original function is f of x equals x to the nth power. And the derivative, f prime, works out to be n, that's the power coming down as a coefficient, and then times x to the n minus 1. N minus 1 is the 1 power less part. Now, it's important to point out, this result, as we might have kind of proposed it and proved it, well, is only valid when n is a positive integer. So this is probably the most basic version for the power rule, that the derivative of x to the n is n times x to the n minus 1. And that's true if n is a positive integer. All right, now we could have powers of x that aren't positive integers. You learned as early in algebra that you can have negative powers of x. They're reciprocals, 1 over x to the power. You can have fractions for powers, x to the 1/2, that's square root of x, and all sorts of powers. So what do we do if we have x raised to a number where the number or power is not a positive integer? Well, that rule that we just stated, what we called the power rule, it works when the exponent is any real number. Now, we're not going to prove that. Again, that's beyond the scope of a good Calculus 1 course, in my opinion. It's basically saved for what comes after the calculus sequence, but we'll just make use of the result. This formula does still apply when x is raised to any power, any real number. So x to the n, the exponent n can now be any real number, and the derivative formula n times x to the n minus 1 is still the correct derivative. So this is what we will refer to as the power rule applying for any real number power of x. All right, and this is where the course, the examples start to look a little more challenging because the functions get more complicated. That's because we're no longer going to rely on the limit definition. Once we get access to differentiation rules, which we are now, some of the problems look like they increase in difficulty. That's only because we have more efficient ways to calculate derivatives than relying on the limit definition of the derivative. All right, so let's get to some examples applying this, the power rule. We might see some examples scattered through the homework with other variables. So the standard variable to use, and again, it's because mathematicians are really boring. We always use x. Now in your science courses, t might be more appropriate, like in physics for functions of time. And later in our course, we'll even see the variable r appearing when we're talking about various quantities related to a circle. Area of a circle, pi r squared. We might be talking about a sphere, volume, 4/3 pi r cubed. So we'll just start to throw in other variables right from the start. So the power rule works the same, just with a different variable. The derivative of t to the n, when we differentiate it with respect to t, we bring the exponent n down, and then we get t to 1 power less. Make sure you see the similarities in the power rule. We're just basically changing the independent variable that we're using. We usually use x, but we will see t and other variables like r occasionally in the near future. So pause if needed to let that sink in. All right, let's move on. Take a look at a handful of examples. So let's say first here we have f of x equals x to the 5th. Now here, I'd like you to pause and see if you can apply the power rule. There's some examples that are simple, and there's some examples that look a little challenging, which we'll be getting to momentarily. So pause and propose your answer for what f prime is here. All right, and if we apply the power rule, we bring the power 5 down, and then we have x raised to 1 power less. 5 minus 1 is 4. So we very quickly get that the derivative comes out to 5 times x to the 4th. Now, just to give you some idea of just how efficient this power rule is, if I myself were to apply the limit definition of the derivative to finding the derivative of x to the 5th, I would have to expand x plus h to the 5th power. That would probably take me several minutes. Now, it can be done if you're really careful, but here we get our derivative, 5x to the 4th, in seconds. So this is a true, legitimate shortcut. But again, it comes from the limit definition. If we never had the limit definition, we would never get access to these shortcuts. All right, let's take a look at a second example. Let's say we have x to the 100th power. Pause and write down what you propose for the derivative here for y prime. All right, we just bring the exponent 100 down and then subtract 1. So our derivative, y prime, comes out to 100 times x to the 99th power. So the power of x really doesn't matter if it's a small power or a large power. The power rule is equally efficient in all cases. All right, let's take a look at a third example. Let's change the variable to t. So this might be when we start relating questions back to position as a function of time, and we start incorporating questions related to velocity and acceleration, the first and second derivative of position. All right, so here we have s of t, that is our function, equals t to the 6th. Pause and see if you can write down what the derivative s prime of t would be. All right, and again, the power rule applies. We just bring the exponent from the function down, 6, and then subtract 1 from that power of t. So we get as our derivative 6 times t to the 5th. Seems really simple, right? How could it get any more complicated? Well, here's square root of x. Pause and see if you can do something to this to turn it into a power. We'll check in a few seconds. All right, that seems a little tricky because you might be arguing, wait a second, Professor Anderson, we're talking about powers of x. That's not a power of x, that's the square root of x. Well, this is one of our first examples where we're going to rely on an incredibly important problem-solving technique throughout pretty much all of mathematics, especially true for the calculus sequence. We're going to rewrite the function. Now, the way we rewrite gets more complicated, but here we can rewrite square root of x as a power, x raised to the 1/2 power. Now we can apply the power rule since we have x raised to a number. The power rule applies to any power. Here we have a rational power, a fraction. So it still works the same way. We bring the exponent 1/2 down, and then we subtract 1 from that. Just be careful with the algebra. This is where I've seen even really good calculus students just get hung up just on basic with fractions. Our exponent in the function is 1/2, x to the 1/2. Now, the way the power rule works is we take the exponent in the function and then subtract 1 from that. So just be careful. 1/2 minus 1 gives you this exponent in the derivative, -1/2. And we're going to start to incorporate some examples. Just with that, the presence of fractions generally makes the problems more complicated for students, but it really shouldn't. Just make sure you're comfortable with that. We're going to be manipulating kind of basic fractions there with subtraction with the power rule pretty frequently from now on. All right, now again with the thought of rewriting, notice our derivative comes out to 1/2 times x to the -1/2. Now we found that by first rewriting the function square root of x as x to the 1/2. Also be comfortable rewriting the derivative back. We have our derivative as 1/2 times x to the -1/2. A negative power, you can put that as a power within the denominator. That 1/2, well, we can think of that as a factor of 2 in the denominator. Recall, instead of multiplying by a number, you can divide by its reciprocal and vice versa. All right, so I can put a square root in the denominator and that factor of 2 as well. So we can rewrite g prime here as 1 divided by 2 times square root of x. And that's an example where you might have been asked to find the derivative, so the derivative of square root of x, using the limit definition. Now, you would have used the conjugate at the time, and it works, but here, rewriting square root of x as x to the 1/2, we get the derivative much more efficiently. All right, let's take a look at another example. All right, pause and give yourself an attempt at this. See what you can determine for the derivative of x to the e power. All right, now this is equally simple as all the others, as long as you make sure you realize e is a number. Here we have x raised to a number. So we can apply the power rule, we bring the exponent down, e, and then we subtract 1 from that exponent. So the derivative here comes out to look a little peculiar, but it fits the pattern from the power rule. We have it as e times x raised to the e minus 1th power. And the power rule does work. All right, we're going to see this appear in an example later in one of the parts for this lecture. Let's take a look at one last final example. Let's say our function here is a fraction, y equals 1 over x squared. Now we kind of gave a hint. It looks like maybe the power rule doesn't apply because this is a fraction. It's not a power of x. Well, take as your hint example 4 here. See if you can first rewrite the function and then apply the power rule. We'll check in a few seconds. So pause if needed and work this out. All right, now what's the trick here? How do we rewrite a fraction, a reciprocal power of x, 1 over a power of x? Well, we can rewrite that as x raised to a negative power. So this is all algebra. Make sure you're, again, very comfortable with ideas from algebra. It might have been a while ago, but it makes all the difference now in Calculus 1. So before we even differentiate, we're going to rewrite our function, 1 over x squared. We'll rewrite it as x raised to the negative 2 power. And now we can apply the power rule. We bring the exponent negative 2 down, and then for the derivative, we subtract 1 from the original exponent. Negative 2 minus 1 gives us now in the derivative an exponent for x of negative 3. So we get as our derivative negative 2 times x raised to the negative 3 power. Now that can be expressed all back as a fraction. That negative power of x, you can put that as a positive power of x within the denominator. And again, just make sure you're comfortable switching back and forth between reciprocal powers, x raised to a negative power, kind of a standard practice for kind of expressing your answers in our course. All right, and that does it for part 1 of this lecture. So we got through part 1 and 2, derivatives of constant functions and the derivatives of powers of x. That's going to be the foundation for part 2, when we'll get to the third part, derivatives of polynomials, which we'll pick up with immediately in part 2.